Good morning, everyone. We'll continue here with a couple Chapter 10 review problems, and we'll get into Chapter 11. Chapter 11 slides are in the lecture slide module. But this question here is out of the Chapter 10 review questions. And so we're looking at air here. We're given its composition. These are the compositions of air by volume. But you can also imagine that this is also, because volume's related to pressure, moles, and temperature, that this would be the ratio, the same ratio of the moles of the particles in air. So the mole ratio of air would be the same as the volume percentage, because moles and volume are directly proportional. Just something we can think about here. We often talk about the percent by volume of air, but this could also be the mole percent of air is also the same percentages, 78% N2, 21% oxygen. So we're asked here, what is the partial pressure of oxygen in a 1.00 atm sample of air? This just comes back to the relationship that a given partial pressure is equal to the mole fraction of a component in a gas mixture times the total pressure. And so the mole fraction of O2 in air is just going to be equal to 0.21, the same fraction of the percent volume. So 21% by volume, 21% of the moles are oxygen, so the mole fraction of O2, 0.21 expressed as a fraction. And so then we can solve for the partial pressure of O2 by taking our mole fraction of O2 times 1 atm. And that gives us, of course, just a pressure of 0.21 atm. So you can see here that the percentage of the pressure that's oxygen is the same as the volume percentage, same as the mole percentage. And so the partial pressure of oxygen, 0.21 atmospheres. So that's the partial pressure of oxygen in air at standard pressure. And then if we said, well, what about the pressure on top of Mount Everest, where, let's say, atmospheric pressure happens to be 253 millimeters of mercury? What's the partial pressure of O2 in atmospheres? So something we might think here is the same basic idea that air is still going to be 0.21 in terms of the mole fraction. The ratio of O2 and N2 is not going to change at elevation. So we're going to have the same composition of air. And so then our partial pressure of O2 is still equal to the mole fraction times the total pressure, but the total pressure now is 253 millimeters of mercury. And we could either convert this to ATM right here, or we could convert or calculate the partial pressure of oxygen in millimeters of mercury and then convert that to ATM. Doesn't make much of a difference, but let's go ahead and convert here. So 760 millimeters of mercury are in 1 atmosphere. So we just need to divide 253 by 760. And so that's 0.333 atmospheres times 0.21. And so now the partial pressure of oxygen on top of Mount Everest would only be about 0.070. So about a third of what it is at ordinary elevation. And so, of course, this is why when you go to high elevation, it's harder to breathe, because you're taking in less oxygen with each breath. Let's look at another review question. This is just looking at calculating densities. We've had quite a few problems that have looked at densities, so you might recall the equation here is that it's pressure times molar mass divided by RT. If you're not sure where this comes from, this is just coming from PV is equal to nRT, and then substituting in mass over molar mass for RT, and then doing some rearranging to get M over V as density, and then just doing the cross multiplication to solve for density. And so density, pressure times molar mass divided by RT. And again, I just like to stress, because sometimes this does appear on tests, that STP is 0 degrees C and 270, which is 273.15 Kelvin, and 1 atm. And it's these values exactly. So those exact pressures and temperatures. So the density of CH4 would be the pressures, 1 atmosphere, right, enough zeros. You can imagine it's an infinite number of zeros. It's exactly 1 atm is the pressure. The molar mass of CH4 12.01, 4 times 1.008, that's 16.04 grams per mole. We've done a few problems towards the end of chapter 10 where we were putting molar masses into kilograms per mole. But what we have to think here is if we want to get grams per mole out, we want to plug in grams per mole for our molar mass.
Is there a reason that you went to more zeros?
Over here, like technically it's exactly 1 ATM. I don't want to write 1 ATM and have us think that it's 1 sig fig. So I just wanted to write enough zeros so that that wasn't going to make me round. But technically it would have, I could keep going with zeros.
Okay.
And so then, and same thing here, like the 0.08206 liter atmospheres per mole Kelvin. We could look this up more precisely if we wanted to. So like really the inputs here are the molar mass and the ideal gas constant, because all the other two values are exact in this calculation. But I wouldn't worry too much about the sig figs per se in this problem. All the choices here are given to us with 3 significant figures. And then 273.15 Kelvin as our temperature. And so I get the answer for A, 0.716. Now how the units cancel, the ATMs are canceling, the mole cancels, the Kelvin cancels. The only units not canceling are the grams per liter. And so that's how we're getting the unit out here in grams per liter. So I do like to circle back to the idea of molar mass units or just units in general. Try to write them, especially in chapter 10, especially in like chapter 3 when we're doing stoichiometry. Writing units will help us prevent mistakes or catch mistakes and just generally know what units things are in. And so then the last question was just coming back or circling back to the van der Waals equation just to talk again about what the A and B values are related to here. And so the A value, it's fixing the pressure due to the molecules sticking together. So the equation, if you need to answer a question with this equation, it's on the test. So you can always look at this equation and see that this is fixing the pressure due to intermolecular forces, and then B is fixing the volume due to the space occupied by matter. So the B value is directly proportional to the size of the gas particle in the gas mixture. And then the A value is directly proportional to the strength of intermolecular forces of attraction. So intermolecular forces, we'll talk about those a lot in the next chapter. So you'll get probably a good idea of what we mean by IMFs when we get into chapter 11. But A is just related to the strength that a molecule is sticking together. So the stickier the molecule, the bigger the A value is. And so A is related to intermolecular forces, and then B is related to the size that the actual sample, the gas particles are occupying in the gas sample. And so if we're comparing O2 and CO2 for the B value, we're comparing O double bond to O, so we have something like this, or we can go to an MO diagram. However you want to picture it, you have a double bond between 2 oxygen atoms. And then for CO2, you have 2 double bonds with a carbon between the 2 O's. And if B is directly proportional to the size of the molecule, which molecule do you think takes up more space? So 1 particle of O2 is certainly going to take up less space than 1 particle of CO2. CO2 is definitely bigger. So we'd expect that CO2 would have the larger B value just because it has more atoms, it's bigger. Similar structure, so 1 double bond versus 2 double bonds bigger. So if we have a mole of O2 versus a mole of CO2, CO2 is bigger, so CO2 will take up more space. So we'd expect CO2 to have the bigger B value. And then if we're comparing CH4 versus water in terms of A value, the A value is getting at the intermolecular forces. And so we have a polar molecule which has that built-in charge. It has that built-in plus minus that gives it that extra attractive force. And then CH4 doesn't have that attractive force. It's a non-polar molecule, so it has a weaker attractive force between its particles. And so we'd expect water to have the larger A value because it's going to have the stronger intermolecular forces of attraction. And we can compare. So we can look for CO2 versus, we were comparing the B value for O2 versus CO2. And so you can see CO2 is bigger than the B value is for oxygen. So we're comparing these two numbers here. And so our prediction worked out. And then we're comparing water versus, I think I circled the wrong one. But water versus CH4, I circled in box in CCl4. But water versus CH4, similar size molecules, but the big difference here is the polarity. Water has that bigger A value due to being more attracted to itself in terms of intermolecular forces. So we get a stronger attractive force between water molecules. This is why water is a liquid at room temperature, but CH4, of course, is a gas at room temperature. We know CH4 is natural gas, and then has a melting point and boiling point well below that of water, or well below that of room temperature. Water is higher because of that strong intermolecular force. So let's get into talking about liquids, because that's kind of what real gases lead us toward, is that once a real gas at low temperature starts to behave like a real gas and a non-ideal gas, then that's because it's starting to approach becoming a liquid. So let's talk more about liquids. So chapter 11 is on liquids, so it's about liquids, intermolecular forces. We try to get a molecular comparison of gases versus liquids versus solids. We look at different types of intermolecular forces, so we can try to look at a compound and try to have some understanding of what types of intermolecular forces it will have, and then predict some properties based on that. And then we do look at some properties like viscosity being one of them. So the sort of resistance to flow of a liquid is related to its intermolecular forces. And so there's some properties that are related. Also, vapor pressure has a relationship to intermolecular forces. The vapors above a liquid can be higher if the intermolecular forces are weaker. So the weaker the force, the less a molecule is held onto in the liquid, the more vaporous it can be. And so we'll get into vapor pressure curves, phase diagrams towards the end of the chapter. Okay, so when we look at the halogens are a great example, because if we look at F2 is the natural occurring state of fluorine, is F2 molecules, but if fluorine is a gas at room temperature, chlorine is also a gas at room temperature. And so if we had a sample of chlorine, we'd have chlorine molecules that would be isolated in a container. As long as it's at a relatively high temperature and pressure, it's going to behave, or relatively high temperature, it will behave like an ideal gas. And then if we have bromine, bromine's a liquid at room temperature. So bromine is one of two liquids at room temperature on the periodic table, of course, mercury being the other. But bromine's a liquid, and it's a peculiar liquid. It's, the bromine itself is a vaporous liquid. It has a orangish color to it. So I don't think you want to sip on bromine or chlorine like 21 Pilots talk about. But I don't think you can sip on chlorine because it's a gas, so that wouldn't work so well. But iodine is a solid at room temperature. So you can kind of see that as you become larger down the period of the halogens, that the melting point and boiling points must be going up. And so we have an increase in melting points and boiling points just because we're approaching a solid versus a liquid versus a gas when we're at the top of the table. And so what must be going on is that bromine and iodine must be picking up a stronger intermolecular force of attraction. If we're comparing these three molecules here, these are all nonpolar molecules. So they're all nonpolar. They don't have built-in charges. And so we're going to have to talk about how nonpolar molecules can have an intermolecular force of attraction. What we're going to see is that they induce a dipole, that they're just going to have two molecules adjacent just kind of push their electrons in such a way that the molecules pick up a charge. We'll talk about that in a moment. But that is presumably going to be easier the bigger a molecule is. That's why iodine picks up the stronger intermolecular force and lasts as a solid to a higher temperature. Or you can think of it the other way around. If you imagine a really hot sample of iodine at a really high temperature and you're cooling it down, it's going to solidify, it's going to liquefy first and then solidify at temperatures well higher than things like chlorine and bromine. Chlorine and bromine at high temperature start lowering them. You got to lower them well below room temperature before they start to liquefy and solidify. We can also have strong intermolecular forces between polar molecules, but it doesn't always, just because something's polar doesn't necessarily make it a liquid or solid at room temperature. HCl is still a gas at room temperature. Like you can buy this in a gas cylinder. Of course, you can dissolve it in water and call that hydrochloric acid, but you can actually buy a gas cylinder of HCl, and it's just individual particles of hydrogen chloride, where they do have a intermolecular force of attraction, but it's relatively weak even though the molecule is polar. So just being polar isn't super great in terms of making something so attracted to its molecule that it becomes a liquid at room temperature, but it's going to make it maybe higher than it would be if it were nonpolar at least. So let's take a look at a few different properties of compounds. We'll talk a little bit more about solids in the next chapter, but ionic bonds have a very strong force of attraction. I think we know this. If you have table salt doesn't melt until about 800 degrees C. So our salts have very high melting points and boiling points, and it's because that ionic bond, that lattice energy between the plus and the minus, is so strong that the covalent bond isn't nearly as strong as those lattice energies are. So ionic bonds, very strong. We have very high melting points and boiling points. Lithium fluoride, really high. Metals often have really high melting points too. Beryllium has a melting point of 1500 degrees C. Interestingly, not shown in this table, but if you were to look at the melting points of the alkali metals, so like lithium, sodium, potassium, rubidium, cesium, francium's radioactive, not one you want to play around with, but in terms of cesium's melting point is like 28 to 30 degrees C. So almost a liquid at room temperature. But lithium's about 200 degrees C. So a lot of our metals actually decrease in melting point as they grow bigger. This is going to be a common trend whenever we're seeing charge being transferred or shared between atoms. Charge likes to be shared between smaller atoms. We saw this with lattice energy. That lattice energies were highest when lithium fluoride's small. If we compare that to cesium iodide, plus minus but big ions, weaker force of attraction because the charges are further away. Same thing with metals. Being smaller allows the electrons to get closer together, be shared better to a stronger sense. So like if we're comparing the melting point of lithium, that it's greater than the melting point of cesium, kind of going the opposite of the trend of the halogens. And again, whenever you see that opposite trend, a decrease in melting point, you can almost be assured that there's some transfer charge going on, because charge transfer, you're going to have a greater attractive force between smaller charges of smaller centers of charge. Make a bigger charge center, less attractive force. Okay, but again, we'll talk more about solids when we get to chapter 12. We'll just cover chapter 12 maybe for a couple slides, so we won't talk too much in chapter 12 about solids and almost just rehashing what we're talking about here. We can also have covalent network compounds that are solids. Like these are things that are common, like diamond, graphite, glass, SiO2, the things in glass. You can have a really high melting point when you have a series of covalent bonds. What diamond is, it's where you imagine a tetrahedral carbon. Imagine methane, but where you have a carbon atom in each of the spots of the hydrogen, and then off of each other carbon, you have another tetrahedral carbon. So you have like a three-dimensional array of tetrahedral carbons all connected together. So that gives you a really strong way of connecting your atoms. That really increases the melting point and boiling point well below what you'd expect for molecular compounds. So CH4 doesn't benefit from what diamond benefits from because it only has covalent bonds between one molecule. The other molecule has covalent bonds, but there's no covalent bonds linking those two molecules together, only a weaker intermolecular force of attraction. So if we then look at some things that only have weaker forces of attraction, like N2, melting point, boiling point of nitrogen, 77 Kelvin. So that's the temperature of like liquid nitrogen, 77 Kelvin. And then if we have dipole-dipole forces, then HCl benefits from being polar, but not so much that it becomes a liquid at room temperature. Notice that its melting point and boiling point are still well below room temperature. Room temperature, of course, is 298 Kelvin. So these are still well below room temperature. So again, being polar helps HCl have a stronger force of attraction, but not so strong that it's like water and it becomes a liquid. Hydrogen bonding is what's really important for things like water and HF. And what you might imagine, if we can have a polar compound, but where we're putting those charges on the smallest possible atoms, that's what makes things like HF, H2O so important, is what we're doing is we're putting relatively small atoms that can adopt partial positive and partial negative charges that are on relatively small atoms, or about as small of atoms as you can have on molecular compounds. So if lattice energies benefit by having the smaller ions have a greater attractive force, same thing here. If we have a polar compound with really small atoms, then we get a really relatively high partial positive charge, allowing that interaction with another oxygen atom to be a much more attractive force, where we get this electrostatic force of attraction. So you get a relatively high plus and minus, strong attractive force in water, stronger attractive force than you'd have if that hydrogen somehow were a different atom and bigger, or if oxygen were a different atom and bigger. So compare this like H2S, H2S turns out to be a gas at room temperature because sulfur is so small, doesn't allow there to be as great of a dipole moment, doesn't allow there to be as great of partial positive negative charges, itself is too big. So being small and being highly charged is good. So HF and water benefit here, and they start to have melting points and boiling points that, or at least the boiling point is above room temperature. So what goes on in samples, like what goes on in things like the noble gases, which have a really weak force of attraction because they're just a single atom. If you're picturing, say, two helium atoms adjacent to each other, you know, helium has 2 electrons. Each of them are filling their shell with electrons. We talked about how if you try to make dihelium, that there's really no benefit to making helium-2 because there's no stable bond that forms between the two. If you think of the overlap of the orbitals, there's no room for the orbitals to overlap. There's no like unpaired electron or empty orbitals. So there's really no easy way for helium to have an interaction with itself. There's no positive or negative end. So what helium has to do is helium has to like adjust where its electrons are and kind of coordinate their motions. Instead of being random, in order for helium to ever liquefy, those 2 electrons just have to shade their motions to the same side of their nuclei. Then you kind of induce a dipole moment. So what we end up doing is we induce a dipole moment where we have a small partial positive, small partial negative, that then is interacting with the other molecules, partial positive and partial negative. So you kind of induce this dipole moment. The electrons correlate their motions. We get a small but important dipole moment that allows there to be a small electrostatic force of attraction that develops between these atoms. But now for helium, this isn't going to happen until about 4 Kelvin. So the melting point of helium is about 4 Kelvin, or excuse me, the boiling point of helium's 4 Kelvin. So almost at absolute 0. The melting point's 1 Kelvin. So we're not going to freeze helium until 1 Kelvin. But at 4 Kelvin, eventually the atoms can coordinate their motions, change where those electrons are, induce this dipole moment. So we call this induced dipole moment a dispersion force. And so all substances can have dispersion forces, meaning all substances can induce their neighboring atoms to induce a dipole moment that's larger than what the dipole moment would be just in an isolated single molecule. And then that dipole moment allows there to be some added attraction between the particles. And so again, we're just trying to create these like small dipoles here. So we're trying to induce where the electrons are in adjacent atoms to create this dipole moment where through the dipole moment, we then get the electrostatic force of attraction. And so then can you imagine if you had 2 electrons in your helium, that this is probably pretty hard, right? And helium has the lowest melting point and boiling point of any substance I believe that we know of. But if you go to neon and argon, what do they benefit from? They benefit from having more electrons. So if you have now 10 electrons here, 10 electrons here, probably going to be a little bit easier to like shift your electrons to induce this dipole moment. So the more electrons you have, the better. The more volume your electrons are spread out over the molecule. If we could have, instead of, say, an argon atom, what if we had the same mass but 2 atoms? That would probably be better. Or what if we had, instead of krypton or xenon, a mass similar but with 2 or 3 atoms, where we spread the molecule out and have a lot more electrons that can be pushed around. Let's take a comparison here of things like neon versus F2. This probably isn't so surprising because fluorine's about double the mass of neon. So fluorine has a lot more electrons. So it benefits by having more electrons, has a higher melting point. Versus argon, it's actually relatively similar. I would have probably thought fluorine would be a little bit higher melting point and boiling point because you're spreading those electrons out in argon instead of around 1 atom, it's now around 2. But you can really see the effect when we compare chlorine, where chlorine's molecular weight is about 70.9 grams per mole. If you compare that to krypton, krypton's 83. So do you see how having a little bit less mass but 2 atoms makes chlorine have a much higher, these are the boiling points. So chlorine has a higher boiling point because it now has 2 atoms to have its electrons spread around the 2 nuclei, and it makes those electrons easier to push around. So the question here is like krypton with krypton next door to it. We get this little point of contact where the electrons can try to shade or shift around each other versus having Cl, Cl, Imagine two chlorine atoms adjacent to each other, so we have now all the electrons in chlorine that can now try to coordinate their motion. So there's like more contact points. The electrons are more spread out, more diffuse, easier to induce that dipole moment. So it's going to be easier to induce a dipole moment in Cl2 than it is in, say, something like krypton. So noble gases have a harder time inducing a dipole moment, even as you go relatively large. If you go to xenon, still a gas at room temperature. So xenon's boiling point still well below room temperature, 166 Kelvin. So still more than 100 degrees C below below room temperature. And then if you look at the halogens, look at how much they're growing because they have that extra atom, they have the extra space. So bromine's melting point goes above that of room temperature, and then iodine's boiling point goes well above room temperature. It goes a couple hundred degrees above room temperature. And so we're benefiting here by adding that intermolecular force of attraction. So we're getting a really strong dispersion force. So even though the dispersion force is a relatively weak intermolecular force, it can be relatively strong if the molecule is big enough. So the dispersion force, weaker but for comparably sized molecules, but if you can just grow a molecule in terms of its molecular weight or size, you can pick up and add to the dispersion force to add to the attractive force between molecules like an I2. So I2 has only this dispersion force of attraction, but it has a relatively strong dispersion force because iodine's molecular weight's really big. It's 126.9 times 2. If we compare that to water, water is only 18 grams per mole, but it gets a stronger intermolecular force of attraction through the dipole-dipole force. But let's look at a couple other comparisons for molecules that are considered to be nonpolar. So are hydrocarbons. Like a hydrocarbon, you can always think is nonpolar for one of two reasons. One, the atoms are all kind of like opposing each other, like CH4 does. You know how CH4 has a zero dipole moment. But also carbon and hydrogen aren't very electronegative. Electronegativity difference is so small that even if you could picture a molecule situated in a way where maybe the molecule could pick up a dipole moment, it still would be very small. So no big dipole moments for hydrocarbons, no matter what their geometries are. And so if we're comparing a linear version of pentane, so pentane has two, or actually has a bunch of isomers, but another isomer of pentane, or the two isomers we can look at here of pentane, are where we have the carbons connected in linear sequence. We call that normal pentane, or just the straight chain pentane. So this is just where you have the 5 carbons connected together. And so a good review for nomenclature is penta for 5 carbons, hydrogens to give us 4 bonds. So we get the formula for pentane to be C5H12. We get the extra hydrogens on the end. But then we can also have a more branched version of the compound where we have like a central carbon, and then we have off that central carbon CH3 groups. And if you notice, that has the exact same count of hydrogens because I have 3 hydrogens on each of 4 branched carbons. You could picture how we have a tetrahedral carbon because I have 1, 2, 3, 4 domains. So that central carbon wouldn't be square planar, it would be tetrahedral. It would look something like the spherical ball that's shown in the picture here. Now this molecule here has the name neopentane. Don't worry about calling this neopentane. I won't ask you how to name this thing. In fact, when you get to OChem, you'll call this 2,2-dimethylpropane, but that's something for OChem, or if you've seen any of that in high school, you might remember that nomenclature system. But anyways, this is just a different isomer of pentane. You might wonder, can we more easily induce this dipole moment in something like N-pentane, or can we more easily induce it in something like the neopentane? Which one do you think? I mean, you could look at the boiling points, I suppose, but don't you see how there's going to be such little contact between the neopentane that it's going to be really hard for those electrons to coordinate their motions to pick up that induced dipole effect. So we're going to have a relatively weak dispersion force, or a weaker dispersion force between neopentane. We're going to have a much stronger dispersion force because we have all these contact points where those electrons can be shifting their motion and inducing their dipole moments. And so the boiling point of neopentane is 309. It's a little bit higher than, it's a good 20 degrees higher or so than neopentane. So neopentane, weaker intermolecular force because it is more branched. So branching impacts our intermolecular force by weakening it. So the more branched a hydrocarbon is, or a structure is, the fewer points of contact there are, the lower that induced dipole moment will be, and then the weaker the intermolecular force. So branch compounds have weaker intermolecular forces. Than linear compounds. So I'll say that again because it's written so terribly. But branch compounds have weaker intermolecular forces, IMFs, than linear compounds. I sometimes wonder why I write anything on these stupid screen other than numbers. So branching weakens intermolecular forces, but we can strengthen intermolecular forces by having a molecule that's more straight chain than branched. But we can also add some dipole-dipole force. So we can just already have a dipole moment. So inducing a dipole moment or inducing a bigger dipole moment gives a molecule a stronger intermolecular force, then having a dipole moment should really help as well. And so what we're comparing here is pictures of solid acetonitrile and liquid acetonitrile. Acetonitrile is where we have a CH3 group and then connected to a CN group, and then the CN has a triple bond. And so nitrogen has a greater dipole moment, picks up a negative charge, and so we have this polar nitrogen group on our molecule giving us a polar molecule. So this is a polar molecule. So polar bond, polar molecule, and then we pick up this dipole-dipole force of attraction. And so we already have the plus minus, and so we can get the plus minus force of attraction. So we're going to get a relatively bigger charge on this side of our molecule, and so then we can have the plus minus attractive force already built into the molecule. We could also induce a dipole moment in this molecule too. So if we're looking at liquid or solid CH3CN, we can say that we have the dipole-dipole force of attraction and dispersion forces going on. So we have dispersion forces of attraction and dipole-dipole forces. So you kind of have like additive forces. So if you're comparing compounds, it's usually best to compare compounds of comparable molecular weight, but if you're comparing something of similar molecular weight to this compound that's nonpolar, you expect that the nonpolar compound to have a lower melting point, lower boiling point. Having this dipole-dipole force of attraction adds to the intermolecular force of attraction and would allow acetonitrile to have a greater melting point and boiling point. We can compare here where we go from propane, which has a molecular weight of 44 AMU, no big dipole moment, 0.1 dBi, so really nonpolar in terms of that molecule, and the boiling point here is the lowest. If we switch this carbon in the middle of CH3, CH2, CH3, if we switch that middle CH2 group to be an oxygen, then that's dimethyl ether, and so that would be where we have CH3, oxygen, CH3, and so that's dimethyl ether, has a dipole moment. Now this is a polar molecule. We see that we increase the boiling point as a result of the molecule being polar, but just being polar doesn't mean it super increases the melting point and boiling point. So notice that the boiling point only increased by less than 20 degrees, but it did increase due to being polar. If we make the molecule more polar by having something like an aldehyde group, now I don't think in every case you can look at a structure and predict that this molecule here is more polar, but you can look at the dipole moment and see it has a bigger dipole moment. So if we're comparing two molecules where one of them has a bigger dipole moment, we would take that to mean that this molecule here is more polar. Again, I don't know if you could have predicted just based on the structure and the geometry of the molecule that it's more polar, but given that it is, you can see that that's a good explanation for why the boiling point increases here. And it increases, in this case, by a fairly substantial amount because we really kicked in the polarity. So the greater we can make a molecule polar, then the more we can increase that boiling point. And then acetonitrile, even with the nitrogen, again, I don't know if you could predict, if I held up a structure of acetaldehyde versus acetonitrile, I don't think you could have predicted acetonitrile is more polar, but given that it has, again, a much higher dipole moment, that means it's more polar, and so that greater polarity kicks its boiling point to be even greater. So the more polar you make a compound, then the greater you make its boiling point. again, where we're relatively similar in size. So we're not changing size here by much at all. So you have to be a little careful to not compare like molecule that's polar with a big non-polar molecule. So we got to compare things that are relatively similar in molecular weight when we're making these comparisons, and also similar in like shape. So we have to compare like a similar branch molecule. So all these molecules have, I think, a pretty similar shape as each other. Well, let's get into then water and HF, things like this, where if you're comparing like melting point or boiling point trends, like let's look at the group that's nonpolar first. So if we look at CH4, SiH4, germanium H4, tin H4, notice that we're just going down the carbon group. So all those molecules form the same type of compound. That the boiling point increases as you go to a bigger atom, and that's just because of the added dispersion force. So all these molecules here are nonpolar, and so we're just increasing the dispersion force due to having a bigger central atom. So the bigger the atom, the stronger the dispersion force, the greater the melting point and boiling point. Okay, and so those are increasing with that trend. And then if we compare, if we kind of for a moment forget about water, HF, and NH3 that are off the chart and kind of look at their other partners, like water would be H2S here, and then this will be hydrogen selenide, and then this will be H2 tellurium. And so if you compare those trends, H2S, H2 selenium, H2 tellurium, you get the increase, and it's really just, again, because of the dispersion force. You're getting this increase here really just because of added dispersion forces. That those molecules aren't very polar. You would probably call them all polar, but they're not very polar. What's different between them is you're just going from essential atoms that's 32 grams per mole to 78 grams per mole to 127 grams per mole. And increasing the size increases the boiling point for the same reason that these molecules here are increasing. If you notice, the slope's about the same. And so then if you compare for like HCl, notice that HCl compared to HF is like still well below room temperature. Room temperature is right here. So right about through where I drew that line is room temperature. So most of these compounds have melting points and boiling points well below room temperature. And really only these three are off the chart. So only those three are off the chart, despite a lot of those molecules being polar but not very polar. But the increase in size increases their melting point and boiling points, but never to a substantial value. But water and HF are off the charts, and NH3 is kind of off the charts too, from where you would expect it based on the other members in its group. Now, what makes these molecules so special is that, again, that's like what we were talking about earlier. They have the relatively highest partial negative charge you can have on a central atom. So they have the most polar bonds you can have because fluorine's most electronegative, oxygen's next most, nitrogen's next, and they're also the smallest atoms. So we're putting the highest possible partial negative charges on those central atoms that we can, and then the hydrogen itself adopts as high of a partial positive charge as we can adopt, and again, it's a relatively small atom. And so we have partial positive charge, those being the highest they can be between any of these compounds on the slide. These are the molecules here where we have the smallest atoms involved, but the most electronegativity difference between all of those bonds. So we create the highest partial positive and negative charges. So we get an especially strong dipole-dipole force of attraction that we call the hydrogen bond. So the hydrogen bond is whenever you have hydrogen directly attached. So whenever hydrogen is directly bonded to N, O, or F, you get this effect. So as long as hydrogen is directly attached to a nitrogen atom, an oxygen atom, or fluorine in a molecule, you get an especially strong force of attraction between those molecules. We call that the hydrogen bonding force of attraction. So if we're looking at a sample of water and comparing it to any other type of compound, like say compare that to like neon, or because it's a pretty comparable molecular weight to neon. Neon only has a dispersion force. Water has the dispersion force. It can still induce a bigger dipole moment than it already has. So it has a dispersion force. Water has a dipole-dipole force of attraction, and it has a hydrogen bonding force of attraction. So it has more types of intermolecular forces and has the stronger of those forces of attraction through that hydrogen bond. That's why water is off the chart. In fact, water can have 2 hydrogen bonds per molecule. You might be wondering, and something you may be thinking about here is, isn't fluorine more electronegative than oxygen? Why is HF not as high as water? But it's because HF can only form one bond. It only has one hydrogen to form a hydrogen bond with. Water has that second hydrogen. And it makes the charge on oxygen be about as high as it is on fluorine, because you now have two oxygens that are, you have two hydrogens that oxygen's stealing charge from, giving it about the same partial negative charge as HF has on its fluorine atom, and then you get that second atom. It leads to the next question, well, why does ammonia not triple benefit from this? But it's a cost-benefit problem. The polarity just drops off because nitrogen's not as electronegative as O or F, so the bond itself's not as polar, and so the third hydrogen bond that you get for NH3 didn't do anything for it. In fact, ammonia has a boiling point still well below room temperature. So ammonia is off the chart from the other molecules in its group, but not really as high as you would expect compared to HF or to water. Now, one last thing to circle back to is notice how there's really nothing special about HCl. Like chlorine's the next most electronegative element. Why would chlorine, which has the exact same electronegativity as nitrogen, why would HCl not be off the chart here even at all? Like, why does it just kind of drop back down and fall in line with HBr and HI? And I think the best explanation would be that it's just too big, that it's the size of chlorine. So even though it has the same pull for electrons, even though it might have a similar partial negative charge that nitrogen has in ammonia, the problem it has is that chlorine's just too big. And so being big weakens that intermolecular force of attraction. So again, being a small atom, being electronegative, having hydrogen as another small atom directly attached is what's required for hydrogen bonding. And so when we're trying to identify which molecules can have the hydrogen bonding intermolecular force of attraction, the key is that the hydrogen bonding force of attraction is the force of attraction between molecules, not within a molecule. So like if I look at CH3F, CH3F would look like this in terms of a Lewis structure. That this is a carbon-hydrogen covalent bond. That's not a hydrogen bonding intermolecular force of attraction. So this is not an H bond. When we think of hydrogen bonding, we're thinking of hydrogen bonding intermolecular force of attraction. We're thinking, when I have these two molecules, which CH3F should be polar, we have this partial negative fluorine, which have a partial positive charge on the carbon side of the molecule. So we definitely have a polar molecule. This molecule here should have dipole-dipole forces of attraction and, of course, the dispersion force of attraction. But it doesn't have the hydrogen bonding force of attraction because I need an H directly attached to that fluorine, not carbon. Since halogens only form one bond, they don't form bonds with two things at the same time. They only bond with one other thing. Practically the only compound involving fluorine that can hydrogen bond is HF, because there's no other way to get H directly attached to the fluorine and have it also attached to something else, because it only forms one bond. So this molecule here, in terms of H bond, force of attraction, doesn't have the hydrogen bond. So A cannot form the hydrogen bonding force of attraction. It may look like it could. You may get confused and say, well, the molecule has a hydrogen bond attached to a carbon. Isn't that a hydrogen bond? But it's not the hydrogen bond intermolecular force of attraction. So we're looking at, when you picture these molecules adjacent to each other, like, what do we think of this attraction here? Is that a hydrogen bonding force of attraction? Not quite a hydrogen bonding force of attraction. If there's a partial positive here, it's not going to be very big because that hydrogen's attached to carbon, which doesn't allow it to have a very big partial charge, not as high as it would be in water, or HF, or ammonia. So we would just call this attraction here either a dispersion force or a dipole-dipole force, but not the H bonding force of attraction. That's really what gets confusing, is you may think the molecule has a hydrogen. Can that interact with the other molecule's fluorine? It can. Or it can, just not through the strong intermolecular force of attraction. If the hydrogen bonding force of attraction was present in this molecule, it would probably have a much higher boiling point than what it does. I don't know the boiling point of this compound, but I do know CH3Cl has a boiling point well below room temperature, and that this compound is even lower. So this compound has a really low boiling point. If this compound had any kind of exquisite H bonding, it would have a much higher boiling point and melting point than what the compound really has. Now, the next molecule, alcohols. Alcohols are great in this regard. They're great in a lot of regards, but the alcohol has a hydrogen atom directly attached to oxygen. That's exactly what we need for a molecule to hydrogen bond. So this molecule will have, ethanol has a hydrogen bonding force of attraction. So if we picture the Lewis structure, we have now an oxygen with a hydrogen directly attached, and it's this partial positive charge is going to be relatively high, and then can interact with the oxygen atom, which is relatively high but partial negatively charged. So if you have a neighboring, I'm not going to draw the neighboring alcohol, but you can have a second molecule of alcohol. Actually, let's draw it real quick. Why not? So if you have the second molecule here, this interaction here, you would call to be the hydrogen bonding force of attraction. So this here would be an H bond. You could call that a dispersion force too. It could add to the dispersion force, so you can call that a dipole-dipole force too. So you can call that or picture that as three different types of forces of attraction. You could imagine that if I flip this molecule on its side, that maybe the methyl chains on the molecule, maybe the H3CH2 group is inducing a dipole moment in itself while the rest of the molecule is participating in a hydrogen bond. So you can imagine part of the molecule is participating in an H bond force of attraction, the other part's inducing a bigger dipole moment through the chain of the molecule. This will probably come up in a slide later, but as you make that chain bigger, if you compare methanol to ethanol to propanol to butanol, remember naming all these things, which one do you think has a higher boiling point, methanol or ethanol? Or propanol? Adding to the chain is going to add to this dispersion force. So the longer we make that chain, the greater the dispersion force, the greater the boiling point. So if we keep adding CH2 group to a molecule, so if we go to propanol, higher boiling point. Butanol, even higher boiling point. So we can add to the boiling point of a compound by giving it more dispersion forces while keeping it with that hydrogen bonding force of attraction. In dimethyl ether, if you recall, that compound didn't have a really high boiling point at all, a little bit higher than propane, but doesn't have hydrogen directly attached to oxygen. So we need H directly bonded to NO or F to have the hydrogen bonding force of attraction. We don't get that in the compound in C. So just compound B can hydrogen bond. So ion dipole forces, we talked about these a lot in chapter 4. I was kind of talking then about how water, I was even saying, well, we haven't seen water, we don't really know what it means for it to be polar, but we now know that water is polar. And so when something dissolves, when an ionic compound dissolves in water, we can now understand that the positive end of water is being attracted by electrostatics to the negative charge on the anion, and then you have the oxygen's negative charge is then being attracted towards the positive charge on the cation. And what do you think? Are you going to get a stronger dipole? Are you going to get a stronger ion dipole force with smaller ions or with bigger ions? Do you want the ions to be bigger or smaller here to have a strong ion dipole force? Smaller. Smaller is better when we're sharing charge. So ion dipole forces inversely proportional to the size of the ion. So smaller ions, greater ion dipole force of attraction. And also, as you would imagine, directly proportional to the magnitude of charge. So if you change sodium to calcium, even better. Calcium has a 2+ charge. We get a stronger dipole-dipole force if we increase the charge on the ion. Now, we probably could get too sidetracked, but solubility comes up as the next chapter in 1220. Chapter 13 that you start in Chem 1220 is on the issue of solubility, so you'll talk about this a little bit more there. But you can maybe address a question from chapter 4, which is, well, why are some compounds insoluble? If all ions can have this ion dipole force of attraction, then why would some compounds not dissolve in water? And you can probably imagine that it really just comes down to, well, what's stronger? Do you get stronger ion dipole forces of attraction, or are the ionic bonding forces stronger in the solid? And you can't always predict. You can't just necessarily look, other than with the solubility chart. But if you didn't know the solubility chart, you couldn't just look at an atom and kind of predict if the ionic compound should have a stronger ionic bond or stronger ion dipole forces. But it just becomes a relative balance between how strong are the ion dipole forces. If those are collectively stronger than the ionic forces of attraction in the solid, then the compound dissolves. Okay, so if we compare intermolecular forces for different types of compounds. If we have just an atomic gas sample, so this is like a noble gas, the only possible force of attraction for atomic gases is for them to have the dispersion force. This is why they're gases. So there's no strong force of attraction between the noble gases. So the only way that they interact with each other is through the induced dipole force, and it never gets big enough even as we go down to things like radon. Radon's relatively heavy, it's radioactive. It can be present in lower levels of houses. You may have seen or heard of like a radon mitigation system. Any of you guys ever heard of this thing? A radon mitigation system, I have one at my house. It's basically just an exhaust fan in your basement. So the reason why you want to worry about radon, especially Ohio has relatively high levels of radon. Radon's a heavy gas, so it's going to settle low because of its density. And so radon's going to settle in your low levels of your house. If you just exhaust your air out of the house and continually replace it, you'll just pump out any of that air and send it back outside. And so, so radon, even though it's really big, still doesn't end up with a high enough melting point or boiling point to make it a liquid or a solid at room temperature, still a gas. If we have nonpolar molecules, if we have something like, and there's so many molecules we could list. We could list things like N2, Cl2, we can even list Br2, I2. We could list things like BF3, CH4, CCl4. These compounds only have the relatively weak dispersion force of attraction. Now, again, if you make the molecule big enough, you can make those dispersion forces be high enough such that the molecule can have a really high melting point and boiling point. So it really just becomes an issue of how big is the molecule. Relatively small molecules that only have dispersion forces will be gases at room temperature. Make them big enough, spread out the electrons more, then you can have a compound that can have a higher set of melting point and boiling points. Polar molecules that do not have an OH, NH, or FH group on the molecule can have the same type of force of attractions here. They have the dispersion force, the dipole-dipole force. If we add in a molecule that can have the hydroxyl group, has an H directly attached to O, an N with an H directly bonded to it, or is HF, then we can have added the hydrogen bonding force of attraction. But notice that we have the other forces of attraction too. So sometimes a question will be, if you're given a substance, what type of intermolecular forces does it exhibit in its liquid state or solid state? The answer would be, if it has hydrogen bonds, it's going to be all three of these. If it doesn't have hydrogen bonds but it's polar, it's just dispersion force and dipole-dipole. If it's nonpolar or atomic, it's only dispersion forces. And then whenever you're picturing an ionic solid, this part here, this chart, I've never really liked this in the book, but the ionic solids dissolved in water, so like NaCl in water, I don't know why they're not checking these two boxes. I think if you have a water sample with a solid in it, the water still has all of its intermolecular forces it should have, dispersion force, dipole-dipole, H bond, and then you add the ion dipole force between the ion. I think the reason why the book wasn't Xing the two middle boxes there was because they were just talking about the ion's interaction with the solvent. So I think they were just talking about the ion versus solvent is only a ion dipole force of attraction, and then it can always induce a bigger dipole moment, so you always get that dispersion force. But the adjacent waters in the sample, the other water molecules between the ions will still have dispersion forces, dipole-dipole, and H bonding forces of attraction. Okay, let me end with this slide here. So this slide here, what it's comparing is kind of a bunch of different compounds that are all relatively comparable in molecular weight, but much different in terms of size, and then the hydrogen bonding that's possible. Let's start down here with radon versus xenon. So radon and xenon, we know those are going to be gases at room temperature. If we go to radon, notice that its boiling point is getting closer to zero, getting closer to room temperature, but still pretty low, minus 61 degrees C. Xenon's a little bit smaller, its boiling point's a little bit lower, minus 110 degrees C. Bromine, having two atoms of kind of the midpoint between radon and xenon, gives it a much, much higher melting point and boiling point. Its boiling point 60 degrees C, melting point minus 7 degrees C, so we get a higher melting point having two atoms instead of one. And so having a bunch of atoms, if we go to dodecane, dodecane is the C11 isomer, I think it's either C11 or C12. But the molecular weight, 170.3 grams per mole, not really polar at all. But notice its boiling point is really high, 215 degrees C. Even if we get up to, I think it's octane, octane's boiling point's about the same as water. So you can replace what would have been a strong dipole-dipole force with intermolecular forces of just the dispersion force, but the molecule has to be very big. So we have a very big molecule here, has a high boiling point and melting point. Notice that the melting point is minus 10 degrees C, so still a pretty low melting point. If we compare that to glucose, 180 grams per mole. It's a single ring here. This isn't exactly table sugar. It's part of what's in table sugar, or it's like half of the sucrose molecule is glucose. But its melting point is 150 degrees C, but we have all these hydrogen bonding groups in the molecule. So that's why its melting point's a lot higher. I'd give you the boiling point, but it decomposes before it boils. So this thing breaks down, caramelizes before it actually boils. So it has a really strong intermolecular force of attraction because we have the same molecular weight, similar molecular weight to dodecaine, but all these H bonding sites. All right, so the more intermolecular forces you have, the stronger and higher the melting point and boiling points will go. All right, we'll pick up from here next time. Have a great weekend.